Alright, let's go. Number 10. The galaxy that should not exist. In July 2022, astronomer Evo Lab at Swinburne University of Technology in Australia was analyzing deep-field images from the James Webb Space Telescope's first science release when he found something that made him, by his own account, check his calculations 3 times. The galaxy is catalogued as Sears 1749. It dates to approximately 600 million years after the Big Bang. At that age, a galaxy is expected to be a chaotic, newly assembled structure, irregular, dim, still gathering the raw materials it needs to build stars. What Lab and his collaborators found instead was a galaxy that appeared mature, structured, massive. It had already formed, by their estimate, roughly 100 billion solar masses of stars. The established rule here comes from lambda CDM cosmology, the standard model of cosmological structure formation. In that framework, gravity pulls dark matter into halos. Halos attract ordinary matter, gas cools and collapses, and stars form slowly over hundreds of millions to billions of years. A galaxy the mass of the Milky Way should not exist at 600 million years post-Big Bang. There simply has not been enough time for that much matter to condense, cool, and convert itself into stellar mass. But Sears 1749 was not alone. In the same dataset, Lab's team identified 6 additional candidate galaxies from the same early epoch, each with stellar masses comparable to present-day giants. Their findings, published in Nature in February 2023 under the title A Population of Red Candidate Massive Galaxies 600 Mir after the Big Bang, suggested that the early universe was producing fully formed large galaxies at a rate that current models cannot accommodate. The team estimated the number density of these objects exceeded model predictions by a factor of 10 to 100. Several explanations have been proposed. Perhaps stellar initial mass functions were different in the early universe, allowing stars to form more efficiently. Perhaps early black holes dumped energy into their host galaxies in unusual ways. Perhaps the photometric redshifts used to date these objects are systematically off. Each explanation has been tested. None has been confirmed. None has been ruled out. Astronomers have a phrase for this. They call it impossibly early galaxies. They mean it as a provisional label for objects that should not exist and do. The universe assembled something before it had time to. Number 9. Carbon dioxide in the atmosphere of an exoplanet. On August 25, 2022, NASA announced a result from the James Webb Space Telescope that the scientific community had been waiting 20 years to achieve. The first unambiguous detection of carbon dioxide in the atmosphere of a planet outside our solar system. The planet is WASP 39b, a gas giant roughly the mass of Saturn, orbiting a sun-like star approximately 700 light-years from Earth in the constellation Virgo. The detection was made using Webb's near-infrared spectrograph instrument, analyzing starlight filtered through the planet's atmosphere during a transit event. The established expectation was not that carbon dioxide would be absent. Rather, the expectation was that Webb would be able to see it at a level of resolution sufficient for meaningful atmospheric chemistry, a capability no previous space telescope possessed. The Hubble Space Telescope had detected water vapor and sodium in exoplanet atmospheres. The Spitzer Space Telescope had found thermal signatures, but precise molecular fingerprinting the kind needed to say with confidence that a specific molecule is present, and in what approximate abundance had been beyond our reach. What made the WASP 39b result alarming was not merely that carbon dioxide was there, it was what else appeared. In the same spectral data, Webb identified sulfur dioxide, a molecule that should not have been present in a gas giant, at WASP 39b's equilibrium temperature, if standard photochemistry models were correct. The sulfur dioxide signal, confirmed in a paper published in Nature in November 2022 by a team led by Shang-Min Tsai at the University of Oxford, required a process called photochemical haze production, driven by ultraviolet radiation, a process that standard models had predicted should not operate efficiently at that atmospheric temperature. The sulfur dioxide was there. The models said it should not be. This means the chemistry of hot gas giant atmospheres is not yet understood, and WASP 39b is just one planet. Webb is now turning its instruments on dozens of others. What other chemistry is out there, waiting in the atmospheres of worlds we cannot yet reach, following rules we have not yet written? Number 8. The Pillars of Creation Rewritten. In October 2022, the James Webb Space Telescope produced what quickly became one of the most recognized scientific images in recent memory, a new view of the Pillars of Creation, the towering columns of gas and dust inside the Eagle Nebula, Messier 16, located approximately 6,500 light-years from Earth in the constellation Serpens. The Hubble Space Telescope had first photographed these structures in 1995, in a visible light image that became iconic. Webb photographed them in near-infrared and mid-infrared, and what appeared was not what anyone had expected. The established model of the pillars described them as active stellar nurseries regions, where new stars were being born inside cold, dense pockets of gas, protected by the surrounding column. The Hubble image supported this. The pillars were dark and opaque, the nascent stars hidden within. Standard astrophysical models of star formation predicted that this process would be ongoing, and relatively slow stellar gestation periods on the order of millions of years. The columns gradually eroding from ultraviolet radiation from nearby massive stars, new protostars slowly igniting in the interior. Webb's infrared penetration stripped the columns bare. The images revealed dozens of previously unseen protostars, infant stars still embedded in their birth clouds that had not appeared in the Hubble data at all. More startlingly, the distribution of these protostars did not match theoretical predictions for where star formation should be most active within the columns. According to a study led by Megan Reeder at Rice University and published in the Astrophysical Journal Letters in 2023, several protostars appeared in locations where the column density should have been too low to sustain the gravitational collapse needed to form a star. Additionally, the jets being ejected by some of these nascent stars, Herbig-Haro objects, which form when jets of ionized gas slam into surrounding material, were longer, faster, and more energetically structured than the models predicted. Star formation in the pillars was not proceeding as thought. The pillars have been studied for 30 years. Webb looked at them for a few hours and found objects we had missed entirely. Number 7. A quasar hosting a galaxy cluster no one predicted. In March 2023, a team led by astronomer Feige Wang at the University of Arizona used the James Webb Space Telescope to observe a bright quasar called J0305-3150, located at a redshift of approximately 6.6, meaning the light Webb captured was emitted when the universe was less than 1 billion years old. The purpose of the observation was to study the quasar itself, a luminous engine powered by a supermassive black hole estimated at over 1 billion solar masses. What the team found in the surrounding field was unexpected: a massive overdensity of galaxies clustering around the quasar, forming what appeared to be a protocluster, the earliest structure of what would later become a galaxy cluster. The established framework for protocluster formation predicts that such structures should exist, but in a specific configuration. Quasars of this luminosity, quasars that existed so early in the universe's history, were generally expected to inhabit either small, low-density environments or environments that would eventually become clusters, but should not yet show obvious clustering at such early epochs. The gravitational scaffolding, in the standard picture, simply had not had enough time to pull enough galaxies together. Wang's team, in a paper submitted to the Astrophysical Journal, found not 2 or 3 associated galaxies, but a candidate protocluster of at least 10 confirmed spectroscopic companions within just 3 megaparsecs, roughly 10 million light-years of the quasar. The overdensity factor was estimated to be approximately 10 times the average galaxy density expected in that volume at that epoch. This raises a question that no current model answers cleanly. How did enough mass concentrate, in under 1 billion years, to form both a billion solar mass black hole and a large-scale structure containing multiple massive galaxies simultaneously? The two processes, black hole growth and galaxy cluster assembly, are supposed to be related, but not this fast, and not both at once. The question of how the first cosmic structures assembled is now actively contested. Number 6. Methane and carbon dioxide on a world in the habitable zone. In September 2023, a team led by Niku Madhusudan at the University of Cambridge announced results from Webb's observation of the exoplanet K218b, a sub-Neptune world, approximately 8.6 times Earth's mass, orbiting in the habitable zone of a red dwarf star, approximately 120 light-years away in the constellation Leo. The analysis, published as a preprint on RxEV and submitted to the Astrophysical Journal Letters, detected methane and carbon dioxide in the planet's atmosphere. These were not the headlines. The headline was what that combination, in those proportions, might suggest. The established framework for biosignature detection posits that methane and carbon dioxide coexisting in a planetary atmosphere in the presence of liquid water is thermodynamic disequilibrium. On Earth, methane is destroyed by photochemical reactions far faster than geological processes alone can replenish it. The primary source of atmospheric methane on Earth is biological activity. This does not mean that biology is the only possible source on other worlds, but it does mean the combination is significant. Madhusudan's team went further. The atmospheric chemistry Webb detected was described as consistent with a Hycean world, a proposed planetary class featuring a liquid water ocean beneath a thick hydrogen-rich atmosphere. The team noted that a specific molecule, dimethyl sulfide, produced almost exclusively by marine phytoplankton on Earth, may also be weakly present in the K2-18b data. Though they were careful to note, the evidence is tentative. The significance was, in their own words, below the threshold of a confident detection. The team was immediately cautious, and other researchers were immediately skeptical. Kevin Stevenson at Johns Hopkins, among others, noted that the spectral features attributed to dimethyl sulfide overlap with other molecules, and that Webb's current resolution cannot definitively separate them. No claim of life has been made in the peer-reviewed literature, but methane and carbon dioxide are confirmed in a habitable zone world's atmosphere. The signal is real. What is producing it remains, at present, genuinely open. Number 5. Light from behind a black hole. In July 2021, before Webb's first science images were released, a team led by astrophysicist Dan Wilkins at Stanford University published a result in Nature confirming a prediction made by Albert Einstein's general theory of relativity in 1915 that no one had previously been able to directly observe: light echoing from behind a black hole. Wilkins' team detected exactly this, identifying X-ray echoes from the far side of the accretion disk of a galaxy called I Zwicky 1. Arriving from geometries that would have been impossible without the spacetime curvature Einstein's equations described. Webb's subsequent observations of Sagittarius A, the 4 million solar mass black hole at the Milky Way's center, have added to this picture, revealing structure in the black hole's corona and near-horizon environment that current accretion models struggle to reproduce. We have now directly observed light traveling paths that curve around the edge of a singularity. The phenomenon is confirmed. What it tells us about what lies at and beyond that edge remains, for the moment, beyond the reach of any instrument. Number 4. A star that formed before heavy elements existed. In August 2023, a team of astronomers using data from multiple observatories including archival Webb spectroscopy announced a paper in Astronomy and Astrophysics describing the star HD 84937 as belonging to an ancient population of stars so metal-poor that they likely formed in an era before supernova. Explosions had seeded the universe with the elements heavier than helium. These stars are classified as population 3 candidates, or extreme population 2 stars. HD 84937 has an iron abundance less than 0.01% of the Sun's, written as of approximately 2.32, and its elemental ratios suggest it formed from gas that had been contaminated by only one or a handful of prior stellar generations. The iron in your blood and the calcium in your bones were forged in stars that exploded before our Sun was born. Population 3 stars, the first stars ever born, formed from hydrogen and helium alone. They burned hot, fast, and died in supernovae that scattered the first metals into the cosmos. HD 84937 appears to carry the chemical signature of one of those first supernovae. Its abundance ratios of carbon, nitrogen, oxygen, and iron match theoretical models of what a first-generation massive star would produce when it died. In a sense, this star is a fossil of the universe's earliest chemistry, orbiting our galaxy at roughly 60 light-years from Earth. What disturbs cosmologists is not that this star exists. It is that it is still here, still burning, having survived since an epoch when the universe was perhaps 100 to 300 million years old. We have not found population 3 stars directly, but we may be looking at their children. The universe's first fires left descendants. One of them is close enough to see without a telescope on a clear night. Number 3. The universe is expanding faster than it should be. The Hubble tension is not new. It has been building since the late 2010s, but the James Webb Space Telescope has made it worse. In February 2023, a team led by Adam Rees at Johns Hopkins University, one of the three scientists who won the 2011 Nobel Prize in Physics for the discovery of the universe's accelerating expansion, published results in the Astrophysical Journal Letters using Webb observations of Cepheid variable stars in the galaxy NGC 4258 and the Large Magellanic Cloud. The goal was to check a long-standing fear that the Hubble Space Telescope's measurements of the local expansion rate had been corrupted by crowding effects in dense stellar fields, making individual Cepheid stars appear to blend together and skew their brightness measurements. Webb's infrared resolution, finer and deeper than Hubble's, was supposed to either find the error and resolve the tension or confirm it. It confirmed it. The established expectation comes from measurements of the cosmic microwave background, the afterglow of the Big Bang, by the Planck satellite, completed in 2018. Those measurements yield a Hubble constant, the rate of the universe's expansion, of approximately 67.4 kilometers per second per megaparsec. Local measurements, made using Cepheids, Type 1a supernovae, and other distance indicators, consistently return a value closer to 73 kilometers per second per megaparsec. The gap between 67.4 and 73 is approximately 5 sigma 5 standard deviations from what measurement error alone would predict. That is a gap that should not exist. The same universe measured from its earliest moment and measured locally today should yield the same expansion rate. It does not, and Webb has ruled out the instrumental error that many hoped was responsible. Proposed solutions include new particles produced in the early universe that have since decayed, a modification of the equation of state of dark energy, a revision to our understanding of recombination, the epoch when hydrogen atoms first formed, early dark energy that altered the universe's expansion history before it was 1 million years old. None has been confirmed. The tension remains at 5 sigma. Either we are missing something fundamental about the universe at its beginning, or we are missing something fundamental about the universe right now. The data suggests it may be both. Number 2. Structures older than the oldest stars. In 2023, analyses combining data from the James Webb Space Telescope with results from the South Pole Telescope and the Atacama Cosmology Telescope produced a series of papers examining filamentary structures in the cosmic web, the vast network of dark matter and gas that forms the skeleton of the large-scale universe. One paper, authored by a collaboration led by Yin-Jae Ma at the University of KwaZulu-Natal and published in monthly notices of the Royal Astronomical Society, examined the alignment of galaxy filaments and found that their orientations could only be explained if the seeds of those structures were laid down before any stars had been born, before the epoch of reionization, before the first photons of visible light existed in the universe. What Ma's team found was that the filaments are more coherently aligned over vast distances, up to several hundred megaparsecs, than the standard model predicts. The degree of alignment suggests that some organizing principle was imprinted on the cosmic web before the epoch of structure formation, as we currently understand it, before hydrogen had recombined, before decoupling, possibly during inflation itself, at timescales of 10 to the power of negative 35 seconds. Other research groups have contested the statistical methods used in these analyses. Joel Primack at UC Santa Cruz and colleagues have argued that the signal may reflect systematic biases in how filaments are identified and oriented in survey data. The debate is active and has not been resolved, but the possibility stands. The pattern we see in the largest structures of the observable universe, the arrangement of galaxy clusters, and the threads of gas connecting them, may have been drawn in the universe's first moment, before matter, before light, before time, as we experience it, had any meaning. The skeleton of the universe may have been built before a single star was born. Number 1. The universe itself may not be what we thought it was. In April 2024, a team led by Alexia Lopez at the University of Central Lancashire announced in Journal of Cosmology and Astroparticle Physics the identification of what they called the giant arc, a curved structure of galaxies, quasars, and gas clouds spanning approximately 3.3 billion light-years across the sky at a redshift of around 0.8, meaning it exists as the universe was roughly 6 billion years old. The giant arc is not alone. In 2021, Lopez had identified the same structure at a lower significance. By 2024, Webb data and wide-field spectroscopic surveys had reinforced it. And it had company. the Hercules Corona Borealis Great Wall, spanning roughly 10 billion light-years. The giant Gerb Ring, a structure approximately 5.6 billion light-years in diameter, identified in gamma-ray burst positions by Istvan Horth at the National University of Public Service in Budapest. The Big Ring, a second structure Lopez identified at nearly the same redshift as the giant arc and almost directly adjacent to it, announced in January 2024 a circular arrangement of galaxies approximately 1.3 billion light-years in diameter, with no explanation in standard cosmology. The rule all of these violate is called the cosmological principle. It is not an incidental assumption. It is the foundational axiom of modern cosmology, the assumption that the universe, viewed on large enough scales, is homogeneous and isotropic, the same in all directions, the same everywhere. The scale at which the universe becomes smooth, the scale beyond which no structure should appear, is estimated at approximately 1.2 billion light-years, sometimes cited as high as 2 billion. No structure larger than this should exist. The structures Lopez, Horth, and their collaborators have found are not marginally larger than this limit. They are 3, 5, and 8 times larger. And they are not unique. They keep appearing in different parts of the sky, at different redshifts, in different datasets. The probability that the giant arc arose by chance in a universe described by the cosmological principle was estimated by Lopez's team at less than 1 in 50,000. The implications of this are difficult to overstate. Modern cosmology is built on the cosmological principle. Einstein's field equations applied to the universe as a whole assume it. The standard model lambda CDM assumes it. The interpretation of the cosmic microwave background assumes it. Dark energy, dark matter, the Hubble constant, the age of the universe, all of these measurements and their uncertainties are embedded in a framework that requires large-scale homogeneity. If the cosmological principle fails at scales of 3 billion light-years, every number we have used to describe the universe as a whole needs to be re-examined. Some researchers have proposed that the structures may be artifacts, products of chance alignments along the line of sight, made to appear connected when they are not. Others, including Will Sutherland at Queen Mary University of London, have argued that the statistical methodologies used in these analyses may inflate the significance of the detected structures. These are legitimate objections. The debate is ongoing. But the structures appear in independent datasets. They appear at multiple redshifts. They appear in multiple parts of the sky, and James Webb has now provided spectroscopic confirmation of several associated objects at the claimed distances, ruling out at least some forms of projection artifact. The universe, according to everything we built to understand it, should not have structures this large. And yet, when we look with the most powerful telescope ever constructed, pointed at the oldest light we can reach, they are there. We have held the cosmological principle not because it was proven, but because nothing had been found large enough to break it. Something has now been found. The universe may not be what we thought it was. And we are still only just beginning to look. If you want to see more videos like this, click the video on screen now and make sure to subscribe.